Okay, so number 21. Which equation represents a valid propagation step in the chlorination of ethene? There are three steps to this. Initiation, where the the Cl-Cl bond is attacked by UV light to produce two chlorine radicals. These guys are going to be moving the reaction forward. There is going to be the propagation step, where the chlorine radical is going to attack one of the particles that are present in the mixture. So for example, if it is ethane, the chlorine radical is going to come in and produce a new radical, which is going to keep the reaction going, and an HCl is going to be formed in the process. For the third step, there is termination, where two radicals now combine together. So for example, if you already have a C2H5 radical from before and a Cl radical from now, it is going to result in a C2H5Cl, thus ending the reaction as the radicals are now out of the system. So for our purposes, we have to find out which of these are propagation steps. D is certainly not the correct answer, as this is a termination step, since there are two radicals that are combining to form one product. C is definitely not the right answer, because our condition is a chlorine radical has to be attacking the reaction mixture. A hydrogen radical is not going to be present in our reaction. Hydrogen radical is therefore out of the question. Our options lie between A and B. Both of these are viable. C2H6 reacts with chlorine radical to form C2H5Cl plus hydrogen radical. Now this is not a reaction that happens. As we know, the larger particle forms a radical, and there is a smaller HCl atom that is formed in the process. So in this example, a hydrogen radical is formed, so this is not going to be our answer. Our only answer that is available to us is C2H4Cl radical along with an HCl molecule that is formed. The answer is going to be B. Malic acid is used in the food industry and for stabilizing drugs. It is the cis isomer of butane dioic acid. So let's start with what this thing is. Butane dioic acid means that there are 4 carbon atoms here. There is carbon-carbon double bond. There is going to be a COOH on top. There is going to be another COOH on top. There is going to be hydrogen, and there is going to be hydrogen over here. Now this reacts, since it's cis isomer, I put both the carboxylic acid groups on top. What is the product from the reaction of malic acid with cold dilute acidified manganate 7 ions? When a double bond reacts with potassium permanganate or any oxidizing agent for that matter, the double bond is going to break, and we are going to get 2 alcohols attached to it. So double bond breaks, OH attaches to one side, OH attaches to the other side. This can be exemplified by seeing the reaction that happens here. C2H4 plus an O group results in the formation of COH, this thing. So this is what happens when oxidizing agent attacks a double bond. Ethane 1,2-diol if ethene is present. So the same thing is going to happen here. So which of these satisfies our condition? This one has OH group on both the carbon atoms that represent a double bond. A. So A is the correct answer. B is not the correct answer, as it no longer has 4 carbon atoms, so 2 of the carbon atoms are missing. This is out of the question. This one is not the right answer, as there is only one OH group that attached to one of the carbon atoms. The other one has a hydrogen attached to it. This is not what happens in our reaction. And this has turned into an oxy group, where there is a carbon atom attached to an oxygen atom attached to a carbon atom, which is not what's happening in our reaction. So this is not the answer. The only option available to us is A. Primary halogen alkanes undergo hydrolysis reaction. Which reaction will occur most rapidly if they're all warm to the same temperature? For this, our first condition is we need a substance that has a weak bond. So CBr versus CCl. Of these two, carbon chlorine is stronger than carbon bromine, so this can be broken down more easily. So anything with bromine is going to react faster than anything with chlorine. So C and D are out of our options. Sodium hydroxide can easily pick up react with C2H5Br compared to water. Since sodium is more reactive, it wants to give away its OH and receive bromine in the process. So sodium hydroxide is going to be reacting more strongly. So B is going to be our answer. For number 24, structural isomerism and stereoisomerism should be considered when answering this question. So we have to consider both what the isomers look like in like their functional groups, the positional isomerism and that kind of stuff, along with cis trans and LD, optical isomerism. So we have C5H11Cl. It exists as two optical isomers. So our first condition is this has to exist as two optical isomers. Let's draw all of these compounds. CHCl, CH3, CH2, CH3, CH2. Our first problem is all of these carbon atoms have at least two hydrogen, so none of these are chiral molecules. This one has two CH3, CH2 groups, so this one is also not a chiral carbon. So there are no chiral carbons in this particle, so this is out of the question because we need to have at least two optical isomers, and for that we are going to need a chiral carbon center. For B, there is carbon, 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 H, Cl, H, 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 H. So for this one, there is a hydrogen here, a chlorine here, a CH3 here, and a C3H7 here. So this is a chiral center. So this satisfies our condition, one of them. And for C, there is carbon, CH3, CH3, hydrogen, carbon, hydrogen, carbon, hydrogen, chlorine, carbon, hydrogen, hydrogen, hydrogen. Did I mess something up? I think I did. I'm sorry about that. Cl is going to be over here, hydrogen is going to be over here, 2CH3 is already gone. So this is what we have. So let's identify this particular substance has a hydrogen over here, CH3 over here, this entire nonsense over here, and chlorine over here. So this is a chiral center. All four are different groups. So C satisfies our conditions. For number D, we have carbon, 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 CH3, CH3, Cl, H, H, tinta H. So we now have a carbon atom. None of these are chiral centers. All of these have the same groups, like at least two of them. So this one has two CH3, this one has two hydrogen, this one has three hydrogen, and these have three hydrogens each. So none of these are going to be chiral centers. So D does not satisfy our condition. So it's going to be either B or C. Now let's get into this one. Only two alkenes are formed. So when we are going to react the chloroalkane with ethanol, like sodium hydroxide and ethanol, it is going to result in an elimination reaction. A double bond is going to be formed. So for this one, we are going to get two possible compounds, CH3, CH2, CH2, C double bond C. There's going to be a chlorine, and there's going to be a hydrogen, hydrogen, and hydrogen. This one does not undergo cis-trans isomerism because the first carbon, where's my eraser? The first carbon has two hydrogen groups. In order for cis-trans isomerism to happen, each of these carbons have to be attached to two different groups. So for this one, since both of them are hydrogens, so there is only one isomer over here. If I change things up, CH3, CH3, CH, carbon, chlorine, and then there is going to be CH3 over here. Now, this has the potential to be both cis isomer or trans isomer. If the chlorine is, there is a chlorine above and a CH3 below, there's a hydrogen above and a CH3, CH3 below. This can be flipped around and we are going to get a new isomer. So there are two possible isomers here, both cis and trans. So one isomer here, two isomers here. The total number of alkenes present is 3. So B is not our option. The only option should be C. Let's check if that is correct. So for C, we now have carbon, carbon, and carbon. There's a Cl over here, CH3 over here, CH3 over here, a hydrogen over here, hydrogen over here, hydrogen over here, hydrogen over here, hydrogen over here. When there is going to be a double bond formed, it's either going to be present to the left or to the right. If it is to the left, there's going to be only one possible isomer over here, since the first carbon is attached to two hydrogen groups. So this only has one isomer. Alternatively, it can be this, where there's a chlorine over here and a CH3 group, and there are two CH3 groups, as the CH3 does not get eliminated in the reaction, the hydrogen does. So there are two CH3 groups over here, so it does not undergo any cis-trans isomerism. So only one alkene is present. One alkene for this isomer, one alkene for this isomer, so 1 plus 1 is equal to 2. So this is the only one that satisfies our condition. So 24, answer is C. Number 25. When warm water is added to halogenoalkane X, an SN1 reaction occurs. AgNO3 is then added, a yellow precipitate is formed. What would be the reaction? A yellow precipitate tells us, like, I'm going to jump the gun a bit. Yellow precipitate makes our lives a bit easier. Chloro, anything with chloro, like silver nitrate, is going to react with chlorine to produce a white precipitate. So chlorobutane is out of our options. Chloromethylpropane is out of our options. So it's either going to be B or D. Now, halogenoalkane X and SN1 reaction has to happen. So in order for the SN1 reaction to happen, it has to be, it cannot be a primary carbocation. So let's see, iodobutane, C, one iodobutane, I, H, and the rest is C3H7. So there is only one alkyl group attached to it. So this is primary carbocation. This is going to undergo SN2 reaction, where the silver is going to attack the iodine directly. The carbon center is positive, the iodine is negative. So the negative nitrate is going to attack the carbon, and then the reaction is going to happen. So this is SN2 mechanism. Iodobutane is out of our option. 2-iodo-2-methylpropane. Let's check what that does for us. Sorry about this. So 2-iodo-2-methylpropane. CH3, I. This is a tertiary carbocation. So the tertiary carbocation is going to first have to break the carbon-iodine bond, and then the nitrate can take its place. So this is going to have an SN1 mechanism where only one particle is present in the rate-limiting step. So the answer is going to be D. Hopefully this video ended up being much longer. Organic chemistry is significantly harder than the other stuff. So it's just going to be 5 questions over here. Hopefully we're going to be able to speed things up as we go forward. Leave any comments that you think is going to improve the quality of the videos. Please let me know what exactly, what criticisms you might have, or what exactly you need help with, so that I can help you out with them. And I'll see you in the next part. Thanks.